Virtual Precalculus. I'm going to help you guys work through some examples from section 10.4 that were particularly troublesome for some of you. I've decided actually to leave out number 17 because it's so much like number 23. So we're going to do 11, 23, and 29. You can go ahead and skip to the part you're interested in. In number 11, we're looking for the fourth roots of unity, and we want it in a plus bi form, otherwise known as rectangular form. Alright? So unity means 1. And the first thing we really have to do is change 1 into polar form, so that it looks like sum modulus r times the cosine of an angle plus I times the sine of an angle. Well, this is actually not too bad because 1 is a real number. When you're working with real numbers like 1 or negative 1, the polar form is always pretty simple. The modulus out front, r, is always just going to be the absolute value of the real number you're working with. In this case, since the number is 1 and the absolute value of 1 is also 1, r is just 1. The angle theta, well, for a positive real number like 1, theta is always going to be 0. Okay? And you can see why that is right here. Because if theta is 0, cosine of 0 gives us 1, and sine of 0 gives us 0. So we get all real and no imaginary. You'll see later in number 23 that for a negative real number, the polar form needs an angle of pi, so that the real part becomes negative. All right? Anyway, our horrible formula on page 647 is what comes in handy here. N is 4, r is 1, theta is 0. Okay, and then k can be 0, 1, 2, 3, whatever, all the way up to n minus 1. In this case, because n is 4, k can be 0, 1, 2, and 3. All right, and so all I'm doing here in black is I'm plugging in what the values are for when k is 0, when k is 1, when k is 2, and when k is 3. Okay, and we can see that all the action is happening in the argument of cosine and sine. In the first example, it's just 0 because theta is 0, and if k is also 0, the numerator of those fractions is just 0. In the second one, well, theta is still 0, but now k is 1, and so 2k pi is 2 pi. And look at the third one. 2k pi becomes 4 pi when k is 2, and 6 pi when k is 3. Alright, so it's really complicated, but if you just focus on one piece at a time and you're careful not to lose anything, it's not really hard, it's just really complicated. Okay, so those are the answers. Those are the fourth roots of unity, but what we need to do now is we need to rewrite them and simplify them and put them into rectangular form. So that's what I'm going to do next. Okay, so that old-fashioned fourth root of 1 out front, that's easy. That just becomes 1, and that happens in all 4 of these. And then I've simplified the arguments. On the left side, you see that 2 pi over 4 has become pi over 2. The third one, the argument has become pi, and the last one, 3 pi over 2. If you don't remember, then go back and see what it started out as, but anyway, the arguments simplify to those things. And these are all special angles. 0, pi over 2, pi, and 3 pi over 2. We know how to find the cosine and the sine of those things. And to go to rectangular form, that's all we're doing. Okay? Cosine of 0 becomes 1. Sine of 0 becomes 0. Cosine of pi over 2, sine of pi over 2 becomes 0 and 1, and etc., etc. And our 4 answers end up being 1, I, negative 1, and negative I, the fourth roots of unity. Number 23, we're looking for the solutions in the complex numbering system to x to the 6 equals negative 1. So what we need are the 6 sixth roots of negative 1. Again, negative 1 is a real number, but because it's negative, what we want to use for the angle in our polar form of this real number is pi, because the cosine of pi is negative 1, but the sine of pi is still 0, so we don't get any imaginary part. And like I said before, what we want to use for r, the modulus out front, is the absolute value of the real number we're using. We're trying to find the polar form of. So the absolute value of negative 1, of course, is 1. Alright? And then we plug everything into this horrible formula. The old-fashioned sixth root of 1 times cosine of this horrible thing and sine of this horrible thing. Do you see where all those numbers came from? Do you see why k is 0 through 5? Okay, make sure all those bits and pieces make sense. Alright, so one at a time we make these sixth roots. What happens when k is 0? Well, those inner parentheses just become pi plus nothing over 6, pi over 6. And that's where this first answer comes from. Cosine pi over 6 plus I sine pi over 6. Whoa, what happened to r? Well, I decided that the sixth root of 1, which is 1, I didn't need to write that anymore, so I just left it out. I'm being lazy, but it's not necessary. Anyway, again, pi over 6 is a special angle. To make this in polar form, all we have to do is evaluate it. Cosine of pi over 6, that's root 3 over 2, and sine of pi over 6 is 1/2. Okay, and then to find the 5 other answers, we just keep adding 2 pi to our numerator, and so our angle changes from pi over 6 to 3 pi over 6 to 5, 7, 9, and 11. Okay, track all this stuff down, make sure it makes sense to you. There's our 6th roots of -1. 29, this one was harder because we're starting out with a number that's not a real number. So finding polar form is a bit more complicated. Again, polar form looks like this. R times bracket cos theta plus I sine theta. And remember there were these little formulas to help us find r and theta. R, it's kind of like Pythagoras, right? It's the square root of a squared plus b squared. And a is -1 for this number, and b is root 3. So as you can see, r comes out to be 2. Finding theta, you can just use one or the other of these formulas, but you have to make sure you get the quadrant right? I mean, it's probably best to use them both. And we know cos theta is a over r, and sine theta is b over r. So again, a over r is -1 over 2, and b over r is root 3 over 2. Well, those should look pretty familiar. To get cosine of an angle to be -1/2, that angle has to either be 2 pi over 3 or 4 pi over 3. Okay, so we have two possibilities, and we can straighten it out by looking at the other one. Sine of theta has to be root 3 over 2. Well, that only works for pi over 3 and 2 pi over 3. Right, so the only one that's common to both of them is the 2 pi over 3. Basically, the fact that cosine is negative and sine is positive is telling us that we have to be in the second quadrant, right? And so it's the second quadrant angle from the butterfly diagram for all these 4 possibilities, right? Anyway, 2 pi over 3 is our theta. So our number, -1 plus I root 3, in polar form looks like this. Okay, and then we're looking for the 4th roots, so we're applying that horrible formula, and it's going to look like this. And k is going to be what? 0, 1, 2, and 3. So let's see how those things look. Alright, if k is 0, then our argument is just pi over 6. If k is 1, then our argument, well, it's kind of complicated, so you might want to flash back to it. But what it's going to end up being is 2 pi over 3 plus 2 pi times 1, because k is 1, all over 4. Okay, now if you work out that complex fraction, that turns out to be just 2 pi over 3. When you make k 2, you end up with 7 pi over 6, and when you make k 3, you get 5 pi over 3. Okay, all of those are special angles. We can evaluate the trig functions there, and we end up with these 4 crazy answers for the 4 solutions to this equation. Alright, and there's really not much we can do to simplify them more, so that's it. Those are the 4 answers. Alright, this is hard stuff, guys, but please don't be intimidated. Take it one step at a time, one piece at a time, and put it all together. I know you can do it.